Today's lesson is a final part of Unit 5 and lesson 5.7. So there are 3 parts to 5.7, and this is the final part. We'll be looking at solving log and exponential equation algebraically. So we'll wrap up this section by looking at a few more questions on how to solve log and exponential equation algebraically. So let's look at the first one. Question 10. This example question. Now, there are 2 ways of solving this question, and the first part, we're looking at using logs. Now, you probably recognize you can use a different method, but they ask us to solve it algebraically. Using log. Now, one of the things you have to remember that if you could write both sides here, you have an exponential. Here's an exponential function, both are equal. But if you could write both sides at the exponent of with the same base, then you can solve without using logs. So I'll show how to do that. Well, this question asks you to use logs. So let's use logs for a minute here. Okay. So step 1, we want to take the log of base 2 for both sides. The reason is because we can change, this is really 2, if you were to write as 2 to 2x plus 2 is equal to 2 power 3 x minus 1. Now, this is the next method, but because it asks you to use logs, let's use logs to solve it, and then we'll use direct method, algebraic method. So next step is to take the log of base 2 for both sides. So take the log base 2 for both sides. So that's step 1. So now what we have here, so initially we have x plus 2 equals 8 into x minus 1. So if we log 2 into 4, x plus 2 equals log 2, 8, x minus 1. Remember, we have this, and we've used these so many times, they're almost part of our strategies. Okay. So we have here now log 2 to the 2. Now this would be 2x plus 2 is equal to log 2 to the power 3 into x minus 1. Similar to what we already have here, but we are asked to use logs. So here we go. So now we have, write this now as an exponential of 2. So now this, it's similar to what we have here. So now we have 2 into 2, so it becomes 2x plus 2 is equal to 3x minus 1. Because we're using this principle here, look at the base, 2 to the 2, so it becomes 2 into x plus 2 is equal to 3 into x minus 1. Then we solve for x. So speaking 2x plus 4 is equal to 3x minus 3. So we have x equal to 7. So that's the solution. Now, to do this algebraically, we'll use this method here. I'll just put a box here. So we have 4 to x plus 2 is equal to 8x minus 1. Now we write both sides with base 2. So we can write this as base 2 because 4 is equal to 2 to the power 2, and 8 is going to be equal to 2 to the power 3. So now this becomes 2 to the power 2x plus 2 is equal to 2 to the power 3, that's 8x minus 1. Now since the bases are the same, the exponents must be equal. So we equate the exponents. So we have 2x plus 2 is equal to 3 into x minus 1. So we have 2x plus 4 is equal to 3x minus 3. So we get x is equal to 7. Same solution. So this is algebraically. And this is using logs. So this is a guideline. Whenever you can write both sides with the same base, then we continue logarithm. When we cannot write them as we'll see in example 12, we cannot write them with the same both sides, an exponential equation with the same base, then we'll have to use log first. So repeat that. If we can write both sides with the same base, then the exponents are equal. If we cannot write both sides with the same base, then we'll have to use logs. But logs could use also to find the solution without going algebraically. But many times algebraically might be easier than the log. Let's go on to question 11. Question 11, we'll do A, which is solve and verify. So the first step you want to do here is to find out where it's defined. Find where both sides are defined. Or the log, find where this log is defined for x. So step 1, we'll write this side here. So consider the values of x for which each log is defined. That's the first step in going on. So for the first part here, we have x must be greater than -7. And for this one here, x must be greater than 1. So x is greater than 1. The next step is to simplify our log. We have log 648 is equal to 6x plus 7 basically the same. So in this case, we can use a product law to simplify. So we have log 648 is equal to the use of product law. So here we use the product law. So this means log 6 x plus 7 x times x minus 1. Now, our next step is to write this as an exponent of 6. So write the exponent of 6 now, it becomes 48. Let's look that nice here. So 48 here. So next step, we write both sides, or take both sides. Exponent of 6. So in other words, write this as an exponential form. So write as an exponential form. So 48 is equal to x plus 7, x minus 1. Next, we will be solving for x now. So solve for x. So I like to write it on side x minus 1. So we have x squared. Bring this over here. So we have equals 0 minus 48. So you have x squared minus x plus 7x minus 7. So it's going to be x squared minus x. No, maybe 6x. Wouldn't it be 7x plus 6x? So plus 6x. 7, negative 7 and 48 mean negative 55 equals 0. Now we're gonna factor. So we have, oops. So x and x. Now 55 would be what? 11 and 5 will give us, yes, 11 plus 11 and minus 5. That's right. So now we have x is equal to 5 or x is equal to negative 11. Negative, this means is extraneous. So negative 11 is extraneous. So x equal 5 is our solution. And you can verify your solution by looking at the right side, substituting 5 into the right side, and verify that it will be equal to log 648. Okay, I'm just going to go through that verification. So you want to verify our solution. So verify So we look at our right side, which is equal to log 6 into x plus 7 plus log x minus 1. So if x is equal to 5, so we have a log 6, 5 plus 7 is log 5 minus 1. This will lead us to log 5 12 6 here. It's log 6 4. Use our product law. Use our product law here to simplify. So we have log 6 12 times 4 is 48. So this is my right side, and the left side is equal also to log 6 48. So that's verifying our solution. Okay, let's go on to question 12. Solve each exponential equation algebraically. Now, this is what I'm talking about earlier. In this example here, you cannot write both sides with the same base. Same as example B, you cannot. So therefore, we have to use log. Okay, so we need to use log because both sides cannot be written. Cannot be written with the same base, with same base. So we have to use log. So have to use log to solve. First of all, let's simplify this. So we can divide both sides by 5. So simplify. So we have 200, 5, 2x minus 1. Divide both sides by 5. So we have what? 5 goes in 24, so be 40 is equal to x minus 1. Next, we want to write both sides, right? Take the log of 2 for both sides. So here, take the log base 2 for both sides. And the reason for that is that we can end up on one side x minus 1 because we are applying this principle again. So if this is base 2 to the power 2, then x becomes whatever value you have, log 40 in this case, over 2. So we have log 40 is equal to log 2 to the x minus 1. All of this now becomes x minus 1. So log 40 is equal to x minus 1. solve for x. So x is equal to log 240 plus 1. Now we'll have a change of base formula here. So we use change of base. So now we apply change of base. Become log base 10. So we have log 40 over log 2 minus 1 is equal to x. And so x is going to be equal to, use your calculator in this case here. I'm going to go, now I'll have to come up a little bit higher. Well, I have log 40 over log 2 minus 1, so log base 10, log 40 divided by log 2 minus 1. You get the answer for, be plus 1. Oops. Plus 1. Just to, okay, redo that. Yeah. So log 40, probably wondering what am I doing here, divided by log 2 plus 1. 6.32 as x. So x is equal to 6.32. So this is very similar to the one we just finished. Notice we cannot write this at both sides as the same base, so we have to use log. So we end up writing, first, write this as log. In this case, we can write it as base 10. So we have 4x. So we have a 10 here, but it's understood. Base 10 is equal to log 6x minus 2. So we use the power law in this case here. So we end up with, for both sides, so it becomes x log 4 is equal to x minus 2 log 6. Well, we use it. So we have x log 4 distributive law here, x log 6 minus 2 log 6. Now we're going to combine like terms. We take the x on the left side, so we have x log 4 minus x log 6 is equal to minus 2 log 6. Combine like terms here we just did, and now we factor out the x log 4 minus log 6. Now we solve for x. So x is equal to negative 2 log 6 over log 4 minus log 6. Now these are all base 10. We can go to our calculator now. And so on top we have negative 2 log 6. Bracket divided by, and we have log 4 minus log 6. give you an answer of 8.83. So we round up to 8.4. So x is equal to, yes, 8.84. We can always verify our solution by substituting 8.84 for x and solve. There are two other questions. They're very much similar to the ones we did earlier. But I'd just like to look at D. That's an interesting twist to this question. So let's look at D for a moment here. So here we have the first step you want to do. This is expand. To simplify, this becomes using the product law. And we want to write this as log 10. Log. Take both sides. So both sides is log base 10. So we have log 3 2x is equal to log 6x. Now here we expand. So we have log 3 plus log 2x is equal to, now power, we have x minus 1 log 6. We are going to have here now log 3 plus x log 2 is equal to x log 6 minus log 6. Combine like terms, we have our x's on one side here. We have x log 2 minus x log 6 is equal to, take the log 3 on the right side, becomes negative. You have negative log 6 minus log 3. Then we can isolate the x here. We have log 2 minus log 6 is equal to negative log 6 minus log 3. Then solve for x, divide negative log 6 minus log 3 divided by log 2 minus log 6. Now we need our good old calculator. And we go to our calculator here, and there's a lot of calculation going on here. So open bracket, so you have negative log 6 minus log 3 divided by open bracket log 2 minus log 6. And then give me a result as x is approximately 2.63. By the way, all the other ones we did are approximate answers, they're not precise. So approximately 2.63 as our final answer for D, which is approximately, by the way. Okay, forget to mention that in the previous ones. For this question here is a similar process as B. Is in this case both sides. So we'll take a log of both sides and solve. Okay, the last question 13 is a very lengthy one, so it might take a little extra time. Question 13. solve and verify, I'll do A. There are two parts to this, but I'll just do the part A. First step, we want to make sure we find for where this is defined. So step one, we find where the value for x are defined in all of the cases here. So step one, we consider the values. Here we go. So consider values of x for which each log is defined. That's the first step. So here, if you look at the first one here, this would be 3.5 because 2x is equal to 7, x is 3.5, so x has to be greater than 3.5. This one, x has to be greater than 1. Here, x has to be greater than -1, and x has to be greater than 3. So x has to be greater than 3.5. Next, we try to simplify. So here we have plus, we will use the product law here. So we have log 2x minus 7, x minus 1. On the right side, we have log x plus 1, x minus 3. Next, we write both sides as exponents. Now we write both sides as exponents. 10. So we have 2x minus 7, x minus 1 is equal to x plus 1. So we have what, 2x squared minus 7x minus 2x give us minus 9x, and that'll be plus 7 on the left side. And on the right side, we have what, x squared minus 2x minus 3. Combine like terms, we'll end up with x squared is minus x squared, and then we have minus 7x minus 7 plus 3. Then we have plus 10. Factor, we have x minus 5 will work there, and x is going to be, yes, be 2. So we have x is either equal to 5 or x is equal to 2. Now, and this is why you need to, because x has to be greater than 3.5, x equals 2 is less than 3.5, so this becomes extraneous. So this is an extraneous solution. So that's your solution. So x minus 2 is extraneous because x has to be greater than 3.5. So far, you didn't encounter any question of this kind, but that's one of the reasons for doing it, so you can actually see the times when finding the values of x for which each log is defined is extremely critical to find the extraneous solution. Okay. Question B is using the quotient rule, very similar. Now the last question, question 14. Here you're asked to solve the equation 10 to the x equal k, where k is greater than 0. So we have here 10x equal k. Now take log of both sides. So now take the log of both sides. So we have log 10x is equal to log k. Use our power law. You have x log 10 is equal to log k. Okay, so we have x is equal to, now log, we know that log 10 is equal to 1, right? Because remember this is 10 here, so 10 to the power 1 is equal to 10. So this here is equal to 1. So we can say that. So this is equal to 1 times x, right? So we substitute log 10 is equal to 1. And if you were to put that in your calculator, you probably could see that. Let's try that. Log 10 is equal to 1. Because 10 to the power 1 is equal to 10 to the power 1 is equal to 10. Is equal to log k. So there you have our final example question.